Hi Bobcats! In this video we're going to look at one of the many variations that can be done on the ideal gas law. We already have a lot of chemistry under our belts, and so we can start combining some of the things that we learned previously with our new information, in this case the ideal gas law. So our objective here is to calculate the molar mass of a sample of a gas, and we're going to do that based on the ideal gas law. Your textbook goes through a little bit of the derivation of this equation, so I'm not going to do the derivation part. I'm just going to show you this equation and then show you how to use it. The funny looking script M stands for the molar mass. So that's what this funny looking script M is. D is the density of the gas sample. The reason I chose this particular font for the molar mass is because a student a while back showed me a little trick. Let's take that funny looking M and I am going to draw a little cartoon from this. I'm going to put in a couple of eyes. We're going to put in a nose and mouth. And we're going to put in some whiskers. And so one of the ways to remember this equation, and hopefully you think that looks somewhat like a cat, maybe give it the little tufts up here on its ears. The kitty cat likes to put dirt over its pee when it uses the litter box. So hopefully that can help you to remember this equation. The molar mass is equal to density times R times T, all divided by P. So let's take a look at using this equation. The equation for the molar mass is that the molar mass is equal to dirt over P. And we almost have the data that we need in this problem. We have a 25 gram sample of gas with a volume of 3.83 liters, a pressure of 1 atmosphere, and a temperature of 0 degrees C. So we don't quite have density, but we have all of the data we need to find density. Density is equal to mass over volume. And with gases, the densities are generally reported in terms of grams per liter. So we can just take these numbers straight. We've got 25 grams divided by a volume of 3.83 liters. So 25 divided by 3.83, and that's going to give us a density of 6.53. And that's in units of grams per liters. All right, I really should make a variable list, but hopefully this is straightforward enough. It's all right for me to skip it this time. We've got 6.53 grams per liter. We're going to multiply that times R, which is 0.0821 liters times atmospheres over moles and Kelvin, and I wrote that decimal point very sloppily, so yeah, that's supposed to be a decimal over there. The temperature is 0 degrees C, but we never use Celsius. We want to convert that to Kelvin, so that'll be 273 Kelvin. Then we're going to divide it all by the pressure, and the pressure is 1 atmosphere. All right, let's check out our units here really quickly. We have atmospheres in the very top and atmospheres in the bottom that are going to cancel out. Our kelvins are going to cancel out with our kelvins. Looks like liters are going to cancel out with divide by liters. So the only units that we're going to have left are grams divided by moles, which is perfect. Molar masses should be grams divided by moles. And so now if I run this through my calculator, I'm going to have 6.53 times 0.0821 times 273, and that's going to give us a molar mass of 146 grams per mole. Now that we are learning so much chemistry, we can start combining things. In an earlier chapter, we looked at empirical and molecular formulas. We were given data about the percent composition of a substance and then asked to find what its empirical and molecular formulas were. Well, that molar mass was a key piece of converting an empirical formula to a molecular formula. So we just learned a technique for finding the molar mass experimentally. So now let's combine all of this stuff here into this one problem. If you look at the end of chapter problems in your textbook, this is problem number 76 from the end of chapter problems. This is going to take a lot of writing, so I'm going to advance one slide where I've got more room to write. All right, on this slide, same problem, just written in a much smaller font. So first thing, let's do the ideal gas law part of this, which told us that the molar mass is equal to the density times R times T over P. And the density of this gas is going to be 1.60 grams divided by 1.55 liters. R is 0.0821 liters times atmospheres over moles and kelvins. And then the temperature is 25 degrees C, but we can't use that. We have to add 273, and we'll end up at 298 Kelvin. And all of that is divided by our pressure of 682 torr, but this needs to be in terms of atmospheres, so I'm going to divide that by 760 to be that conversion. All right, you may want to do some of these calculations in parts. If you're not real comfortable running that through your calculator all at once, hopefully I get it through successfully the first time. And I ended up with a molar mass of 28 grams per mole. All right, so now we know the molar mass. Let's take a look at that percent composition data. To find the empirical formula, we assumed that we had 100 grams of each substance, so those percentages became directly gram amounts. So we have 85.63 grams of carbon, and we have 14.37 grams of hydrogen. We need to convert these to moles because formulas are always written in terms of moles. So we want to turn grams of carbon into moles of carbon. So for every 12.01 grams, we have 1 mole. We want to do the same thing down here with hydrogen. We want to convert grams of hydrogen into moles of hydrogen. And so let's see, for every 1.01 grams of hydrogen, we have 1 mole. The 1.01 and the 12.01 just simply came off of the periodic table. All right, let me run those numbers through my calculator. 85.63 divided by 12.01. That's going to be equal to 7.13 moles of carbon, and then 14.37 divided by 1.01 is going to be 14.2 moles of hydrogen. We want to divide through by the smaller number, which would be 7.13. So when we divide through by that smaller number, we end up with a ratio here of 1 mole of carbon to every 2 moles of hydrogen, or we would write that as simply CH2. If we go to the periodic table and look up masses for that, carbon is 12, hydrogen is 1, but we have 2 of them, so the empirical formula mass, or empirical formula weight is 14, but our molecular weight was 28. So if we take that molecular weight or our molar mass of 28, and we divide it by our empirical formula mass of 14, we get 2. So that means we need to take this empirical formula 2 times to get the molecular formula, and I didn't leave myself room to finish this out, so I'm going to bring that over here. Say, all right, if I take that twice, I have 2 carbons and I have 4 hydrogens. So that will be the molecular formula for this compound. So in this video, we looked at how you could find the molar mass of a gas sample, and we talked about how that looks like cat ears over on the left-hand side. So the cat likes to put dirt over its pee to help you remember that equation. And then we also explored a couple of examples that showed how we're now learning so much chemistry that we can connect it back to things we've learned previously in all sorts of cool ways. Eat 'em up, cats.